Let's just do a couple of more examples of this fundamental theorem of calculus part 2. We're going to find an antiderivative of x squared minus 4 and then plug in our limits from 1 to 3. So I have x squared minus 4. Let's find our antiderivative. We're going to add 1 to the exponent, divide by the new exponent. So I'm going to get x to the 3 divided by 3. Antiderivative of a constant, we're just going to put a variable on the constant. So we're going to say minus 4x, and we're going to evaluate from 1 to 3. And again, usually when I've got more than one term in my antiderivative, I turn that evaluation bar into a set of brackets just so I remember to plug into my entire antiderivative. Again, we get to skip the plus c anytime we're doing a definite integral because this works for any antiderivative. We pick the simplest one that has a plus 0 as the constant at the end. All right, let's plug in our x equals 3. So I'm going to have 3 cubed over 3 minus 4 times 3. Plug in our bottom limit and subtract. So 1 cubed over 3 minus 4 times 1. All right, so let's go ahead and evaluate these. In my first set of brackets, I've got 27 over 3 minus 4 times 3 is 12. Then I've got 1/3 minus 4. So the 27 over 3 is going to be 9 minus 12. Then I've got a minus, I'm going to distribute that negative sign. I've got a minus 1/3 plus 4. So let's lump all of our whole numbers together. 9 minus 12 will give me negative 3, plus 4 is going to give me 1. So I've got a 1 minus 1/3. And just to combine those, let's make that 3/3 minus 1/3, or 2/3. All right, let's go check our answer over on the applet. All right, I have our function graphed here, x squared minus 4, and we've shaded the area from 1 to 3, and GeoGebra got the same answer we did, 2/3 is equal to 0.67. And look, there's a fair amount of area here, but remember we have some of it being negative below the x-axis, some of it being positive above the x-axis, and there's a whole lot of that area that's just canceling out. So it turns out that the positive area is just slightly bigger, only by 2/3 of a unit, than the negative area. Last example for the videos today, integral from 0 to pi over 4 of secant theta, tangent theta, d theta. Again, variable doesn't matter as long as it matches the variable of integration, d theta there at the end. So we need to find our antiderivative of secant theta, tangent theta. So you may want to go back and look at that list of antiderivatives that I gave you in section 4.10. Secant tangent is the derivative of the secant function. So our antiderivative for secant tangent is secant. So we have, this is equal to secant theta. And we're going to evaluate that from 0 to pi over 4. So we're going to plug in pi over 4. So I get secant pi over 4 minus secant 0. All right, so time to look at the unit circle. Remember that secant is 1 over cosine. So we're going to have 1 over the cosine of pi over 4. If you look at pi over 4, that's the 45-degree angle in the first quadrant of your unit circle. And the x-coordinate, or the cosine of pi over 4, is root 2 over 2. And then we're going to do 1 over cosine of 0. So of course, 0 is the right-hand side of your unit circle, and the x-coordinate over there is 1. So cosine of 0 is 1, secant is 1 over 1. All right, so let's do a little keep change flip on that first fraction. So I've got 1 times 2 over root 2 minus 1 over 1. And then, so that's just 2 over root 2 minus 1. And that's going to be good enough. It turns out if you rationalize that 2 over root 2, that's actually going to simplify out to just the square root of 2. So this is actually the square root of 2 minus 1, which is a much nicer looking answer, but I'm fine with the 2 over root 2. Here we are in the applet graphing secant x times tangent x, and I've got the limits going from 0 to pi over 4, and the GeoGebra applet rounded off pi over 4 to 0.79, and it got an answer of 0.42. If we type in our square root of 2 minus 1, it's actually 0.41. GeoGebra rounded off that 0.79, so it got a slightly different answer than we did, but that's okay.